Okay.
So if I told you I was going to send you stuff
Jacob.
to a L'Hopital.
So, L'Hopital's rule only works when we've got indeterminate form of 0 over 0 or infinity over infinity, positive or negative. Okay? Take a look at this one. What's the sign of 0? Say it?
0.
0. Plus 1, so it's 1. To the power of cotangent of 0. Cotangent of 0 is cosine over sine.
That's 0.
No, cosine over sine.
That's in
No, cotangent of 0 is 0.
So it's cosine of 0 over sine of 0. Obviously, we're not plugging in numbers at 0. We're plugging in numbers really close to 0 on the positive side. This and cosine of 0 is 1. Sine of 0 is 0.
Oh.
1 divided by 0. In fact, it's 0 on the positive side. So it's 1 divided by a very, very tiny positive number. Okay. So it's going to get very, very large. So what is this effectively becoming close to?
Infinity.
What's that?
Infinity.
It's 1 to the power of a very large number.
1.
So you say. No. You pick a number, I mean, it's two things that are happening here. It's 1 that's a little bit bigger than 1 to the power of infinity. 1 to any power we would say is any finite power. We'd say is 1. A number to the a very large number, we usually say either it's going to 0 or it's going to infinity, depending on what number you're raising to the infinite power. But in this case, we're raising a number that's bigger than 1, just slightly bigger than 1, to the power of infinity. So it's fighting it between being an answer of 1 and infinity. Does that make sense? Okay. We can't use L'Hopital's rule as is, but we're going to tweak it so that we can. Any suggestions on how we might tweak it?
We somehow need to make it a fraction.
Yes, we somehow need to make it a fraction. We somehow need that exponent to go away or move somewhere else. How do you do that?
You can,
If we take the natural log of something, exponents turn into multiplication, right? Okay. So a good way to do this is say y equals 1 plus sine of 4x to the power of cotangent of x. Okay? We've got the limit as x approaches 0 on both sides here. So what's the limit as x approaches 0 on the positive side of y?
Why is it from the positive side?
Because they said so. Remember how we're dividing by 0 on this one for cotangent?
Yeah.
Okay. If they just said it's approaching from both sides, then this is either approaching positive infinity from the positive side, or if it was approaching from the negative 0, it's going to be coming close to negative infinity. So that would be undefined.
Okay.
Does that make sense?
So
That's the reason why they chose 0 from the positive side?
They could have chosen 0 from the left side though.
Correct. And then it would be going to negative infinity.
Okay.
Which might be a little bit more clear on what would happen. Well, actually it wouldn't, but we could still figure it out. Limit of 1 plus okay, so you suggested taking the natural log of both sides. I would agree with that.
Where do you do that again? Where do you put it in the limit?
After the limit before limit.
After the limit before the... Okay.
We would do the natural log over here, but limits allow you to move in and outside of a function, so there's not a problem there. So we can just say it's the natural log of y right here. And then when I take the natural log of this one, I can immediately bring this down in front as multiplication.
Wait, so would you be adding the limit of x approaches 0 of cotangent of x?
Say again?
Like, would you be why are you multiplying and not adding? Because like when you're adding natural logs, that's multiplication.
Let me add another page here. Natural log of x to the power of y is equivalent to y times the natural log of x. Do you want me to prove that to you?
No, I believe me.
Okay, now what?
We still can't use L'Hopital's rule, but we could.
But did you say natural log of x to the y or x to the y? Yeah.
Alright. There you go. What did you say? I'm sorry. So I know what to do, but I want you guys to think about it.
Turn cotangent into cosine over sine.
It is cosine over sine, yeah. You can think of that way.
Okay. But sine of 0 is 0, so that doesn't help. That would just be that where we start.
As x approaches 0, it's a good idea to take a look to see what's happening with these two things that are multiplying. Do you see that there's two things multiplying here? Okay. Cotangent of x as x approaches 0 from the positive side, what is this getting closer to?
Positive infinity.
Positive infinity. What about this guy?
One plus 0. That's just approaching 1.
No, because the natural log of 1 is 0.
This is approaching the natural log of 1. Natural log of 1 is 0, so this is approaching 0. So it's 0 times positive infinity, right? Okay. This should feel like a previous problem that we did. We've got multiplication going on. 0 times any number, we say, any finite number, is 0. A large number times any other number besides 0, we say, is a large number. So we've got a fight going on between these two functions right here.
We can do natural log over tangent, and that would be the same thing.
That would be the same thing. So we can do the natural log of 1 plus sine of 4x over tangent of x.
Tangent of x.
We just did the reciprocal of cotangent of x, right?
Tangent of 0 is
Just
0.
like we did on the previous problem, remember? On that one, we have, in this one we have the limit as x approaches 0 of x times ln of x. As we're approaching 0, this is the first term, x is getting closer to 0. ln of x is getting close to infinity, or negative infinity. And remember we made it as ln of x over 1 over x. We did the reciprocal of the thing. Do you remember doing that? We did. We wrote this one as this yesterday. We did. We had a purpose for doing that. What was our purpose of doing this? This is equivalent to this. Everyone sees that?
And it puts it into indeterminate form.
It puts it into an independent. It puts it in the form that allows us to use L'Hopital's rule. This top part now is going towards negative infinity, and the bottom part's going towards infinity. We can now take the derivative of the top and the bottom and figure out what this limit's going to become. The reason why we didn't do it with ln of x, put it as 1 over ln of x, is because then we'd have to take the derivative of 1 over ln of x, and we found that that doesn't simplify anything. So, We're back to here. Why is this a good form?
Because we can take the derivative of the top and the derivative of the bottom.
Can we?
We can.
Why?
Because that's what L'Hopital's rule says. It says that if you have indeterminate form, and
Do we
that's-
have indeterminate form?
We do.
Who checked it?
I did.
You did? In your head?
We did.
We did?
We all did.
I didn't. Did you?
Well, natural.
Did you, John? Did you check it?
I'm working on it.
Okay. Let's check it and make sure if we have it in indeterminate form.
Sine of 0 is 0, 1 plus 0 is 1, natural log of 1 is 0.
Yeah, so this top part is approaching 0. The bottom part.
Tangent is sine over cosine. Sine of 0 is 0, cosine of 0 is 1, that's 0.
0. So both approaching 0. Good. It's indeterminate form, which means we can take the derivative of it.
Let me just study for it.
Of each part.
Chain rule.
One over 1 plus sine of 4x times the derivative of the inside, so that's going to be cosine
Yeah.
4x
Times 4.
times 4 all over the derivative of
Secant
tangent.
squared.
That is annoying.
Yep.
So,
But wait, secant
Hang on.
squared of x is still 0. Secant of 0 is still 0.
Secant of 0 is 1 over cosine.
Hold on, cosine of 0 is 1. Never mind, we can plug in 0 now.
Can we?
We can.
Check it out. Plug in 0 here, we get 0, and that becomes 1.
Uh-huh.
This becomes cosine of 0, 1, times 4, 4 over 1. What's the answer?
4.
Yay. Isn't that good? 1 to the power of infinity.
I see no exuberance.
I mean, it's cool. I'm tired.
Partake in it, or we will send you to the Ministry of Love.
1 to the power of infinity is effectively what we have. It's an indeterminate form, but it's not of a way that we're going to be able to use L'Hopital's rule immediately. But we can move that infinity down in front.
Hang on. What we have right here is the natural log of y equals 4.
Oh, thank you. Yes.
The limit as x approaches 0 and the natural log of y equals 4.
Thank you for stopping me on that.
Oh, come on, we're not done yet.
We're almost done.
We just need to do algebra to it.
This is equal to 4. Right? Okay, what was y equal to? Y is equal to this. Okay. The limit as we do this, so what do you think the answer is going to end up being here? What's the answer of the limit?
And again, it does 4 equals 4, and that doesn't tell us anything.
What's this? 'Cause that's really what we're looking for. I'm not writing out y, I'm writing this whole thing right up here.
Isn't that 4?
What's that?
Isn't that just 4?
The limit as x approaches 0 from the positive side of ln of y is what we figured out to be 4. So what's the limit as x approaches 0 of just y?
A natural log of 4?
How would we get rid of this natural log here?
You can pull it
E.
outside of the limit.
I can pull it outside the
And then
limit.
you take e to that power.
E to that power.
So you take e to the 4.
E to the 4th.
Okay.
Thanks for catching that. That's a big one.
What is e to the 4th?
I don't know, it's a number. 2.7 to the 4th.
Yeah, I don't understand how you got from that step to that step.
Okay, how do I get rid of a natural log? I raise both sides to the e power.
Mm-hmm.
Okay. By the way, I can pull this ln out front of the limit,
Right.
okay?
So that's the natural log of y. No.
So it's natural log of the limit as x approaches 0 of y.
Oh, okay.
Okay, it still equals 4.
Mm-hmm.
And then if I raise both sides to the e power, then I get this.
Oh, okay.
Okay? Or the way I just think of it is just raise both sides to the e power. I don't think about moving that outside there. I just know that the limits can move inside and outside of functions that are continuous. Yes?
54.59.
54.59. So 1 to the power of infinity, in this case, is 54.6.
6.
Is that right?
5.598.
Yeah.
So it's about 6.
5981503.
Weird.
It is weird.
It is weird. And if I change this to some other function, I could get some completely different answer. Okay? Any questions on this?
How do we check our answer? To see if it's plausible
You could plug in numbers really close to 0
without doing that.
without doing that.
Yeah.
You could just plug in one number that's really, really close to 0.
Like 1.000000001.
Make sure you're in radians mode too. Okay, let's do this one. I love this function. It's so cool. Okay. 0 to the 0 power. Anything to the 0 power is 1. 0 to any power is 0. Which one wins? Oh yeah, it's an indeterminate form of 0 to the 0 power. How do I solve this?
We could try taking natural log thing
Yes.
Yay!
So we say y, our thing, equals x to the x. The question becomes, what's the limit as x approaches 0 from the positive side? Jacob, why did they choose from the positive side?
Because you can't take the square root of a negative number.
Correct. And so
X to the
you
x.
have some decimal power up here, which is effectively some kind of root. At some point you're going to have a root, and then you have some negative power.
X to the x has a positive domain.
Yes, x to the x has a positive domain. Actually, it has some negative domains.
But it's isolated points, right?
Right, it's not continuous at that point. Like -3 to the -3. That works, right?
Mm-hmm.
So there's random points that work. It's very spotty on the left side. So it's not continuous on that side. So we're just going to look at the positive side. Of x to the power of x. Okay? Equals, let's take the natural log of both sides. Limit as x approaches 0, positive side. The natural log of y equals the limit as x approaches 0 from the positive side of x ln of x. You guys okay with me skipping that step? I brought that x that was up there right in front.
Mm-hmm.
John, you okay with that?
Yeah.
Okay. What form do I have now? This is 0 times this. What? This should look very familiar.
Natural log of 0 is infinity.
Natural log of 0 from the positive side, as we approach 0 from the positive side, becomes negative infinity. Not positive infinity.
Oh, okay.
Do you see why?
Mm-hmm. No, I do.
Okay, times 0.
So we can change the x to and divide it by 1 over x. Or negative infinity divided by
Congrats. Continuing on. What should I check before I do this next step?
They have L'Hopital's rule.
L'Hopital's rule applies, so
Infinity over.
negative infinity over positive infinity,
Mm-hmm.
it works. Why don't I want to put this as 1 over ln of x?
Because
that
that's
has-
ugly.
And then when I take the derivative, it's not going to be really nice. So take the derivative, I get 1 over x for the top part. Can you guys take the derivative of the bottom fast? No?
Negative 1 over x squared.
Good job. Okay.
Well, crap.
Well, I've got infinity over infinity. Sorry. Yeah, infinity over infinity again. I can use L'Hopital's rule again, can't I?
Mm-hmm.
So should I?
Yes.
No,
Why not?
because you can simplify it.
Because I can simplify it.
Oh,
It
right.
becomes
That's just
x,
negative x.
Negative x squared over x, which is negative x.
The problem with this one right here is I couldn't simplify it, but when I took the derivative, I can simplify it. Don't blindly do L'Hopital's rule.
Yeah, Jacob.
Okay. By the way, if I do L'Hopital's rule, it took the derivative of this, I get negative 1 over x squared. This one I get 2 over x cubed. Do you see how the exponents are going to get bigger and bigger every time I do L'Hopital's rule?
But I have a question.
Mhm.
If we do, because though that does fit the condition for L'Hopital's rule.
Correct.
So if I do use L'Hopital's rule, and I find the answer to that,
Yes.
like immediately, like I don't use it again. I use L'Hopital's rule one more time,
Yes.
and I find the answer to that.
Yes.
Will the answer to that be the same as if I use L'Hopital's rule one more time?
Absolutely. We talked about that previously. You can use L'Hopital's rule you can use L'Hopital's rule properly as many times as you want.
Can we do it like for this problem?
If you want to.
I do want to,
Okay.
because I do.
People who are watching this at home, this is stupid.
You recording?
Yeah.
Oh man.
That's the derivative of the top. Derivative of the bottom is 2 over x cubed. It's a horrible 3. I don't even know how to fix that.
It's like a cursive L.
Or an I or something.
Can I send a message?
Okay.
Can I send a message?
Can I do L'Hopital's rule again?
You could,
Hmm?
but can we not?
Sure, we cannot. Let's simplify this. So this is 2 fractions dividing by each other, so it would be
Oh, the 2 goes on the bottom. I see. So it's negative x over 2.
uh-huh.
And then, yeah.
And that equals 0, right?
Yep.
Are we done?
No.
Nope. Remember, it's the limit as x approaches 0 from the positive side of ln of y. So
That's e to the 0.
it's e to the 0 power. So y, which we defined, is going to be e to the 0 power, which is 1. So the limit as x approaches 0 of x to the power of x, on the positive side, is 1. Yay! Which one wins? The exponent wins,
In this case.
in this case.
What if we have x to the x to the x?
We can do it.
We can.
Sure. Go ahead.
Can't do it off the top of my head.
You do it. Okay. It's an interesting function if you graph it. I won't have you graph it now. In fact,
Don't look ahead, Rachel. Don't look ahead. Stop looking ahead, Rachel.
save it until you graph it, because you can graph it without using the graphic calculator. You have everything you need. This looks so cool. Why not?
I saw it.
The minimum is the most interesting thing about it, I think. Yeah, you can look it up, you won't know what it is. But it's very interesting. Okay,
Well, that's-
any questions on this? Alright, let me give you your homework.